Okay, we're going to go back and we're going to start at the beginning of the book. We're going to talk about thermodynamics for a week or so. And after we do that, we're going to learn about statistical mechanics that will tie what we did with molecules, atoms, and their energies to thermodynamics, which is looking at the properties of big bulk systems of atoms and molecules. So we're going back to the beginning, and this is actually just a little section before focus one on energy, temperature, and chemistry. And we talked a little bit about this as we learned about quantum mechanics. So we can talk about almost everything in chemistry in reference to energy, energy moving, the energy of a structure. Um, and what we want to think about at all times is what we learned in quantum mechanics, that energy can't just take on a continuous any amount of, of energy into a system. So we looked at this picture when we talked about quantum mechanics and spectroscopy, looking at rotational states, vibrational states, electronic states, and translational states, and how much energy can go into each of those modes. So we'll continue to think about that idea, especially when we get to focus 12, which is statistical mechanics. Within statistical mechanics, what we'll learn is that the population of any one of these states is going to be proportional to E to the minus the value of that energy, so the energy of the state, divided by KT. So it's really a measure of whether or not at the temperature you're at, and you multiply it by K, which is Boltzmann's constant. That's a fundamental property of a system, KT. And so whether or not a state is populated is really what's its size of energy relative to the temperature you're at. So in focus 12, we're going to learn a lot about this, but at high temperatures, you have many, many high energy states populated versus at low temperatures, you're often in just the ground state, sometimes a few other states populated. But that's going to be an important thing to think about when we do statistical mechanics and look at the relationship between the energy of a state and the temperature we're at, and looking at the population of those states. So thinking about why temperature is important when you talk about energy, just going to read this last little paragraph essentially. At low temperature, matter survives unchanged. So when we're at low temperature, you don't tend to have enough energy to break bonds to make new molecules. But if we're at high temperature, some molecules have such high energy that they can undergo change. This feature is also hugely important for chemistry, for it enables chemical reactions. So Boltzmann's distribution underlies the two major aspects of chemistry. So Boltzmann's distribution was this idea that the population of a state is proportional to e to the minus energy of that state divided by kT. So the Boltzmann distribution underlies the two major aspects of chemistry: the persistence of structure when you're at low temperature, and the possibility of change when you're at high temperature. So as we go into thinking about bulk systems and relate them back to molecules at the end, the first thing we want to do is think about what is our system. And in general, when we go through thermodynamics, we use the perfect gas law as our model because we're going to see it has such a nice equation of state. It's easy to use mathematically. So when we talk about the properties of a gas is a form of matter that fills whatever container it occupies. And so we're going to talk about the perfect gas. We're going to talk about a little bit the kinetic model of gases. I'm going to tell you how we'll learn that. And then we'll talk about a real gas. All gases are real, but we can approximate them with a perfect gas model when we're at low pressure. So the perfect gas that we want to start with, we'll find that we have a system, and we can describe that state of that system by knowing the volume, the pressure, the temperature, and the number of moles. So these are all things that we've talked about in some other chemistry class. So the volume, just how much space the substance takes up. And this little section talks about some of the units. You want to try to use SI units always. And that will just make your life easier because all SI units are consistent, so you won't have to think so much about whether or not units will cancel. We have the pressure. Pressure is a measure of gas particles hitting the walls of the container, and it's the force of those collisions per unit area. So force of those collisions per unit area as the gas molecules are bopping around and hitting the walls of the container. Again, a big discussion about the units that you can use. Temperature, we're going to use the thermodynamic temperature, which is the Kelvin scale, which says absolute zero, the lowest temperature you can have is T equals 0. The Celsius scale does not have the same 0 degrees, so things freeze at 0 degrees, but you can go below that, so you can have negative Celsius. We don't want to work with that. We want to work with the absolute scale. So we're also going to need to remember about amount of substance, which in the perfect gas law, which we're going to talk about here in a second, will always be given in the units of moles. Talks about extensive and intensive properties. So something extensive depends on how much you have. That's something like the mass. If you have a big container of substance and you have the mass of that substance, if you take a small bit of it, it would have a different mass. But if you took all small bits in the big bit, you get them all to add up to the extensive property. Other properties can be intensive, things like temperature. If you have the temperature of a big system, measure the temperature of each little bit of it, you wouldn't add them up to get the whole temperature. So those are just when we think about substances and their state, we'll use those words sometimes. So the interesting thing is that V, P, T, and N are not independent. So if you know 3 of those, you know the 4th one. So mathematically, that's like equation 4 here that just says pressure is a function of N, V, and T. So if you mix a quantity in a container of a certain volume at a certain temperature, you can't determine the pressure. The pressure is set by an equation that relates all of those. And so the reason why we're going to be so focused on the perfect gas law is because most substances don't have known equations of state. So the equation of state would be exactly this functional form right here. How does the pressure depend on N, V, and T? So for most things, liquids, solids, you don't have an equation of state that will tell you that relationship. But for a perfect gas, you do. So for a perfect gas, PV equals nRT. So that's equation 5a. You've seen it before. So that says that pressure is a function of N, V, and T, and the proportionality constant is R, which is a gas constant, which you can measure experimentally. Table right here gives you that gas constant in lots of different units. So depending on your circumstances, you may use different units. It's not always convenient to use SI units with the gas constant, but sometimes it will be. So the perfect gas law is an example of a limiting law. So it's only valid for gases when you're in the limit of low pressure, then it's a perfect match. But at high pressures, when you have a lot of substance, you'll start to have deviation as the molecules can interact with each other. So there are hypothetical substances that could obey this law at all pressures, but in general, a real gas only will obey this law at low pressures. But lucky for us, if you're an atmospheric chemist, if you're studying gases at the pressure of the Earth's surface, in general, it's a pretty good approximation to say that they're perfect gases. And so everywhere in this text, Adkins will assume, if he doesn't tell you otherwise, that the gas is behaving as an ideal gas. So the perfect gas law was developed with a bunch of experiments. One was to show that pressure is proportional to 1 over volume. That's Boyle's law. Another was Charles' law, which shows that volume is directly proportional to temperature. And then the last one, Avogadro's principle, that says the volume is proportional to the number of moles. If you put all of those together, you can get the ideal gas law and end up with the proportionality constant between all of those things is equal to R. This is just a graph showing you that pressure versus volume is a parabola. So each of these lines is a different temperature. So the shape of that line looks kind of like a half arc. And so it's hard to determine if you have a perfect gas looking at these. You wouldn't really be able to see if it deviated from that behavior. So most common thing we're going to do, and is done a lot in physical chemistry, is to try to find a way to not graph P versus V, which is a parabola, but to graph something that will make a straight line. So it turns out if you graph P versus 1 over V, you'll get a straight line. And when you get that straight line, then it's easy to see how far you deviate. So you can get an equation for that line. You can see if your data is a perfect fit. So trying to find a way to express the relationship between physical properties in such a way that you should get a straight line is going to be the easiest mathematical way to see what your error is. That's really all in this toolkit you need to read. I find this other stuff past here is confusing, and it won't be really necessary, so you can skip it. So this is just showing the difference, plotting P versus V, the parabola, plotting P versus 1 over V, you should get a straight line. And then you can start to see, in this case, for example, at what pressure does the observe start to deviate from a perfect gas, things like that. So it'll be much, much easier to see whether or not your data is a perfect fit or not if you've changed it into that relationship so that it should be a straight line. Let's just use the perfect gas law. This will be very, very easy for you and fun after doing quantum mechanics. So self-test 1A.1 says calculate the molar volume of a perfect gas at 0 degrees and 1 atmosphere. So we have PV equals nRT. I rearranged it. The molar volume is just the volume divided by the number of moles. So if I have V over N over here and RT over P over here, I have temperature in Kelvin. The problem gives me 1 atmosphere. So I picked a gas law that would give me molar volume in decimeters cubed per mole. So you can look back at that table on the first page of the focus to see what kind of units might be easiest to use right here. And when I did this problem, then I got 22.41 decimeters cubed per mole. And this had 4 sig figs. When I add this to 273.15, this will have, because this is a 0, this will have 4 sig figs. So our answer should have 4 sig figs. So this table is not particularly helpful talking about the molar volume of different gases, except to show you that they're all exactly the same. So independent of what gas you have, because for a perfect gas, we're thinking nothing's interacting, size of the particles don't matter. So each of these gives almost exactly the same molar volume. And this is when we're at 1 bar. These two things I will never use, just because it's the only time you ever use these concepts of standard ambient temperature and pressure and standard temperature and pressure. So one of them is just at 25 degrees and one's at 0 degrees and 1 ATM. So I would just give you the temperature, pressure that I want you to use rather than name them as standard ambient or standard temperature and pressure. So let's do another problem. How do you use the ideal gas law? Pretty sure you'll find these problems easy. So self-test 1A.2 says calculate the pressure exerted by 1.22 grams of carbon dioxide confined to a flask of volume 500 decimeters cubed at 37 degrees Celsius. So we want the pressure. So we just start with PV equals nRT and move the volume to the right-hand side. We're going to need to take our mass of carbon dioxide and make it into moles. That'll have 3 sig figs. Our volume is 500 decimeters cubed, which is the same as a liter. And our temperature in 37 would be 310 in Kelvin. So I put all of that in, number of moles, gas constant in units. That will cancel everything. Let's just confirm that's true. Yeah, and we're going to end up with atmosphere. So then when I solve that, I get 1.41 times 10 to the minus 3 atmospheres. So just a problem to start you practicing keeping track of your units. Let's just go ahead and do this next problem. So they want us to calculate the final pressure of a perfect gas that's compressed from a volume of 20 decimeters cubed to 10 decimeters cubed and cooled from 100 down to 25 if its initial pressure is 1 bar. So this will just make you remind yourself of how you deal with a problem like this where it doesn't tell you the number of moles. So we have a question of what's the final pressure. What's the final pressure? Gives us the initial pressure, the final, or the initial volume, the final volume, the initial temperature, the final temperature. And so, and also the initial pressure. So we know that the ideal gas law will be true for both the start and the finish. So if we rearrange this, that means that if I take everything to one side that's changing, that means pressure initial, volume initial over temperature initial will equal NR. And NR is a constant. So even if we don't know what N is, we know it's going to stay constant. So that has to be equal to pressure final, volume final, temperature final. So even without knowing number of moles, we know this has to equal this because this is a constant. So to figure out the final pressure, we can put in our initial pressure, our initial volume, have to put the temperature in Kelvin. Each of these you could put in any units you want, pressure and volume, because to convert those to other pressures and volume is a multiplication. But to convert between Celsius and Kelvin is a sum. And if you have a number plus X divided by a different number plus X, that plus X is not going to cancel as it would in each of these conversions. So temperature has to be in Kelvin always. The other things, I can have whatever units are consistent. So pressure initial, volume initial, temperature initial, or temperature final, temperature initial, volume final, and I end up with 1.60 bars. So this is a common way to essentially extrapolate out from, or extract out from the ideal gas law, any individual relationships, whether it's the relationship between P and V, when number of moles and temperature are constant, whatever it is, you can just set your expression equal to the constant and solve that way. So you probably remember If you have a mixture of gases, you can also use the ideal gas law. And so when we talk about a mixture, the total pressure would be a sum of all the individual pressures, and each of those partial pressures would be equal to the mole fraction times the total pressure. So those are two equations that you would remember from Dalton's law of partial pressures. The mole fraction is simply the number of moles of a component divided by the total number of moles. And so if we try self-test, self-test, yeah, 1A.4, let's read that. So it says, the partial pressure of oxygen in air plays an important role in the aeration of water to enable aquatic life to thrive and in the absorption of oxygen by blood in our lungs. Calculate the partial pressures of a sample of gas consisting of 2.5 grams of oxygen and 6.43 grams of carbon dioxide with a total pressure of 88 kilopascals. So let's see. So we have 2.5 grams of oxygen. So we have 7.81 times 10 to the minus 2 moles, 6.43 grams of carbon dioxide. So 0.146 moles of CO2. So the mole fraction of O2 would be the moles of O2 divided by the sum of the two moles of oxygen and CO2, and we get 0.348. So if that's the mole fraction of oxygen and you only have two components, then you have to have them add up to 1. So that means the mole fraction of CO2 would be 1 minus the mole fraction of oxygen. So that's 0.652. So then the partial pressure of each of those gases is just the mole fraction times the total pressure, mole fraction times the total pressure. So I got 31 kilopascals of oxygen and 57 kilopascals of CO2. Oops, I somehow lost the page here. Should be one more page. Let me go quickly and see. I must have left it stapled. Just take me 1 minute. Sorry about that. So the last thing is just to point out that we have to think about the difference between perfect and real gases. And so we'll learn more about what it means to say a gas is real versus perfect when we go into that section here next.